Good afternoon. Hello, my name is Daniel DeBaba. I'm from University of Tennessee Health Science Center, the Department of Tennessee Clinical and Translational Science Institute, and the Preventive Medicine. Today, we'll discuss about meta-analysis and systematic review. The objectives of our today's presentation includes defining meta-analysis, describing the advantages and the disadvantages of meta-analysis, describing the steps in meta-analysis, and discuss the fixed and random effect models. Meta-analysis is a statistical procedure that integrates the results of several independent studies considered combinable to develop a single conclusion that has greater statistical power. So to combine several original studies, the studies have to be of the same study design. We can combine cohort studies with cohort studies. We can combine case control studies with case control studies, and randomized controlled trials with randomized controlled trials. So the studies have to be combinable, and usually we conduct meta-analysis when we have two or more published or unpublished studies. The conclusion is statistically stronger than the analysis of any single study due to the increased number of subjects, greater diversity among the subjects, or accumulated effects and results. So the conclusion based on meta-analysis is stronger than the conclusion of any single study. So in the hierarchies of strengths of evidence, at the top we have meta-analysis, specifically if the original studies are randomized controlled trials. The evidence from meta-analysis of randomized controlled trials is stronger than the evidence from any individual other studies. So the evidence from meta-analysis is stronger because we get a large number of participants than individual studies. So when we design individual studies, we usually go through the design stage where we estimate the sample size that would enable us detect the difference between the compared groups. And also we assume certain statistical analysis power, usually 80%, and we assume about the alpha level, which is a probability of the chance that difference exists, usually taken as 0.05, and duration of comparison and the likes, the number of sites and the likes, and so we estimate the sample size. Sample size from individual studies, when they come together in meta-analysis, they give us more statistical analysis power, statistical power than individual studies. Meta-analysis allows objective appraisal of evidences. We get forest plots. We look at the 95% confidence interval, how varied the estimates are in original studies, and we estimate the heterogeneity between studies. We look at whether there is some kind of bias in the original studies. So meta-analysis and systematic review give us objective appraisal of evidences. Meta-analysis provides a more precise estimate of the effect size using forest plots and pooled effect size. Meta-analysis provides a more complex analysis of harms, safety data, and benefit. May explain heterogeneity between results of individual studies using the Cochrane chi-square and the I-squared statistics. Let's look at the advantages and disadvantages of meta-analysis. A meta-analysis provides greater statistical power. It helps for confirmatory data analysis to confirm the significant association in some studies are actually hold, they are robust. So when we include multiple studies, we can confirm whether there exists association between exposure variable and the outcome variable. It has a greater ability to, it provides a greater ability to extrapolate the result to general population. Since multiple studies from different regions can be included in meta-analysis, the result from meta-analysis can be generalized to more than a single population. So it's more generalizable than the results of single studies. Meta-analysis, as I've said earlier, is considered evidence-based resource. The evidence is stronger than many other sources of evidence. The disadvantages of meta-analysis include the related difficulty in conducting the meta-analysis and the time it takes for collecting the appropriate data and identifying the appropriate studies. And the fact that not all studies provide adequate data for inclusion and analysis. Some studies provide a point estimate and the p-value, but you need the variability around the point estimate. If the study have been published very recently, you might reach out to the authors and get original data, additional data for conducting the data analysis. But in some cases, you can't communicate, you can no longer communicate with the authors, so you cannot include study that you think is relevant. So not all studies provide adequate data for inclusion and analysis. Meta-analysis requires advanced statistical analysis techniques, but one can learn it. There are a lot of software out there. Some of those are like the Statistical Software, which is an open source statistical analysis software, and STATA, which is an enterprise-based statistical software that one can subscribe to. You can buy a license for a few computers for about $200, $300 and they use it for many years. Another one is Revman 5. We'll look at those statistical analysis techniques at the end. So meta-analysis requires advanced statistical analysis techniques. And the other one is heterogeneity of study populations. If the study population have a lot of variability, sometimes if the estimated effect size are highly different, sometimes it doesn't make sense to conduct the meta-analysis. It's better to just leave the study as they are. You can review the study in systematic review. So for example, if the studies are conducted in children and the population of children and adult population, it doesn't make sense to include these two studies in the same meta-analysis. All the combined studies should be of the same design: randomized controlled trial, cohort, case control, cross-sectional design. The study should include both studies with positive, negative findings, and studies with no associations, and published as well as unpublished studies to avoid publication bias. So publication bias in meta-analysis is that when like most studies that are published either identify a positive association or negative association, and based on the hypothesis of authors or journal editors, sometimes they might trash and reject the manuscript that do not find any significant association. So you end up having studies that only find significant association between the exposure and outcome of interest, whether that is positive or negative. So when we leave out studies that do not find a significant association, we run into what is known as publication bias. There are ways to assess publication bias in meta-analysis. The most common one is using the funnel plot, and also formal tests using the Egger test and Beggar's tests, which provide us p-values. So in meta-analysis, there are several steps involved. The main ones are formulation of the problems to be addressed, the research topic, and why it is significant, collection and analysis of data, a reporting of our results. Let's look at each one after the other. So formulation of the problem. In the formulation of the problem, including in the background and the introduction, describe the health problem in terms of magnitude, prevalence, incidence, and trend. Prevalence means the old plus new cases of a health condition. Incidence means only new ones. And trend means the variability across times and periods. And describe the public health importance of the health problem or its priority for the public health. And describe the level of the risk factor or the exposure in the population. So for example, if we look at type 2 diabetes, at this moment, globally, over 400 million people have been affected. And it's estimated that at the 2050 or 2030, the number increases, the number keeps on increasing. And a lot of cost is also involved. So there is obvious public in terms of magnitude and importance for the public health. There is a huge priority there. Cardiovascular disease is the same. Cancer is the same. So describe the level of the health problem that you are about to study. Describe the outcome in detail in the introduction and in the background. Describe the level of the risk factor as well. So for example, if we talk about obesity in the study population, again, describe what is the prevalence, what is the incidence, how is that related with the outcome. Links the risk factor and the outcome through literature review. So why do we conduct meta-analysis? The reasons why we conduct meta-analysis includes inconsistency of results. So if the results from individual studies or regional studies are inconsistent, we have to conduct a meta-analysis. So, and when more than one studies have estimated the effect size, but the effect size are not combined before. So if multiple studies have been conducted and there are inconsistent results, and then we conduct meta-analysis rather than adding many other studies. So when there are inconclusive or unconvincing previous meta-analysis and new primary studies have been conducted, we conduct a revised meta-analysis or meta-analysis. So why don't we compute the average of effect sizes or add the data from all the previous studies? The reason is that, so different studies have different sample sizes, and they have estimated sometimes different effect sizes, and the variances vary from study to study. So we cannot give the same weight to each study. And we give more weight to studies with more participants and more events or outcome and lower variance. Let's take up an example. An example of averaging the effect estimates in the 95% confidence interval on the association between coffee consumption and the risk of type 2 diabetes. So we have 5 studies that were generated here. We have point estimate, relative risk, and the lower limit of the 95% confidence interval and the upper limit of the 95% confidence interval. So in the first study, the point estimate is 0.7, and the 95% confidence interval ranges between 0.44 and 1.12. In the second one, the point estimate is 0.76, and the lower 95% confidence interval ranges between is 0.59 and the upper is 0.98. In some studies like here, we have the 95% confidence interval that covers 1, and here again. So if we do a simple average, we are giving the same weight to each and every study. So the studies with very narrow confidence interval, which means the study has larger sample size or highly powered, gets the same kind of weight when we rely on just average. So the average is, so adding all these point estimate and dividing by 5 gives us 0.704. And for the confidence interval, it gives us between 0.53 and 1.02. So when we do in a state a meta-analysis, we give different weight to the studies based on the variability and the sample size in the study. Here, the weights is based on the inverse variance. For example, the study with the ID of H has a weight of 57.5, and the first study has about 2% weight. So the studies are given different weight based on the variability that they show in the original data. So for example, in the first one, the 95% confidence interval is very wide, and it covers the null hypothesis value of 1. In the third study, in H study, the 95% confidence interval is very narrow. So that means this study has a less variability, and it's given higher weight. And the same is true for this one, because it has a narrow 95% confidence interval, it's given a weight that is relatively larger. So when we look at the pooled effect estimate and the 95% confidence interval, there is a significant association between coffee consumption and the risk of type 2 diabetes here, with the point estimate of 0.65 or the risk being lowered by 35%. And 95% confidence interval ranges between 0.61 and 0.69. This is in contrast to 1.02 in the previous page, when we just did the simple arithmetic average of the point estimate and 95% confidence intervals. So, like I said, when studies have larger sample size and larger number of outcomes, those studies are have higher weights in meta-analysis. They get higher weight automatically by statistical software in meta-analysis. So for example, study conducted by Clifton on hypothermia and days as compared to in control group, there was no significant difference over the time of follow-up. And the next year, Clifton again conducted another study in larger number of participants. This study gets a higher weight. And other studies with larger sample size, like here, they get more weight. So the total weight adds up to 100%. This add up to 100%. Another example of why we don't do a simple arithmetic average of effect size and rather conduct meta-analysis. So for example, in this study, we have the original data in the experimental group and the control group, the outcome. So the study is on the steroid administration in any dose against no steroid administration, and the outcome is days at the end of follow-up period. And so when we compare the outcome in the experimental group to the control group, we get, if we just add up the columns, we get the average of 34.3% versus 32.5%, a relative risk of 1.06, a higher days rate in the steroid group. But when we conduct a meta-analysis, when a meta-analysis is conducted, we get a relative risk of 0.96, which is relatively lower than 1.06, a lower days rates in the steroid group. So the next step in meta-analysis is, so the first step is you have to convince that you have to describe the relevance of the outcome, the magnitude of the health outcome in the exposure level. And you have to convince the reviewer and editor why meta-analysis is relevant. And so there have to be original studies that have inconclusive results or inconsistent results. And once we have multiple studies, we want to aggregate the data and give a unified result. So once we have done that, we collect and analyze the data. Collection and analysis of the data is another step of meta-analysis. So where do we get the data? The data for meta-analysis are indexed in, come from studies indexed in PubMed, which is the National Library of Medicine, which is maintained by National Institute of Health of the United States. And it gets data studies primarily from Medline, but also from other journals. So we search the PubMed, Medline, EMBASE, the Lancet, Web of Knowledge, and Cochrane Library, and the Scopus, ScienceDirect, Web of Science, and reputable journals like British Medical Journal, American Journal of Medicine, New England Journal of Medicine, Nature, Cell, and the likes. And once we, so first we have to write our search criteria. In the search criteria, we have to include keywords that helps us identify the exposure, studies based on the exposure, based on the outcome, based on study population, and years of publication and the likes. And the outcome or effect measures like mean difference, Cohen, and relative risk, odds ratio, hazard ratio, proportion, and the likes. And based on all those keywords, we create our search criteria and search original studies in PubMed and other study databases. And once we have done that, once we identify relevant studies, we search reference lists of the identified studies, and also hand search in Google Scholar. And the study units in meta-analysis are primary studies, unlike the original studies where study units are individual participant. in meta-analysis, the study units are primary studies. We have to describe the inclusion and exclusion criteria and make sure that we don't run into publication bias. And so our exclusion criteria has to be something that has to be defensible. And we have to specify the exposure and outcome, and the exposure and outcome have to be clearly defined. So for example, if we look at vitamin D intake, how is the vitamin D intake defined? What is the dosage? What is the frequency of intervention? And what is the follow-up period? So we have to clearly specify those. And study design and quality, whether if you want to conduct a meta-analysis on a cohort study, you should exclude cross-sectional studies and the likes. If the meta-analysis on intervention studies, make sure the meta-analysis, the analysis aspect includes only those from randomized controlled trial. You can include different methods, but the analysis group has to be different. So you can't combine one study with cohort design with another study with randomized controlled trial. The year of publication is another. And sometimes people make restriction about the year of publication. Older studies might not be as good as the recent studies. The quality of the study might have changed. The definition of exposure, the definition of outcome might have changed over time, and so older studies might be inappropriate to include in the current meta-analysis. So you might put some kind of restriction of year of publication. Appropriate measures of effect size, like mean difference, standardized mean difference, Cohen's d, odds ratio, relative risk, hazard ratio, proportion, and with their 95% confidence interval. So you should include this in your description of the inclusion and exclusion criteria. Adequate data should be available to extract or to compute for the meta-analysis, for a study to be included in the meta-analysis. And the studies should be as similar as possible. For example, studies conducted in children should not be combined with studies conducted in adult population. Studies should be non-institutionalized. If the participants in original studies are institutionalized, there might be some changes that might confound the relationship between the exposure and outcome. So if you want to conduct a meta-analysis on participant in institutionalized setups, you have to include entirely the institutionalized study participant or studies with institutionalized study populations. So we don't mean here you shouldn't conduct a meta-analysis on participant in institutionalized setups. We are saying when you combine studies in general population with institutional population, there can be some source of confounding. So for example, the food might be different. The physical activity in institutionalized population might be different. So many confounders can affect the association between the exposure variable and the outcome variable. The types of data extracted. So we'll describe the data extraction and study selection criteria. Under the data extraction, we'll we will extract the author's last name, the year of publication, the sample size in the original studies, the age of participant, sex, the duration of follow-up, if there is a follow-up, the exposure assessment method, the definition of the exposure, It has to be very clear. The exposure category and adjusted confounders or potential confounders, the definition of the outcome variable, and the assessment of outcome method, the outcome assessment method, and the measure of the effect size. Again, this should be extracted and included in your in tables. So summarize your data in tables and describe your study selection with graph. So in your graph, you would describe as the search technique using the keyword is showed, let's say 1,000 original studies. Among those, maybe 700 have been excluded because they don't study the association between the exposure of interest and outcome. And then further, you exclude studies that do not have relevant data for the meta-analysis, and also exclude studies that are reviews, that are previous meta-analysis, and studies that were conducted in animals and the likes. And then finally, probably you end up with only 10 original studies for your meta-analysis. So you describe those study selection procedure in graph. And finally, you you prepare your data in Excel, the summary of your original studies in Excel, and you can import your Excel data into statistical softwares for the meta-analysis and conduct your meta-analysis. So the meta-analysis, the final meta-analysis includes the summary, the author name, the year of publication, the point estimates, and the 95% confidence intervals of the original studies. And also it contains the weight given to each study based on statistical analysis methods. So there are two statistical analysis methods for meta-analysis, fixed effects and random effects models. We'll look at each in the next slides. So when we say the fixed effect model, this model assumes all the studies were estimated a single effect size, and if sample size were infinitively large, the studies should give the same result. They should arrive at the same result. This model gives a narrow confidence interval. It assumes that variability is due to chance. So in fixed effect model, the weights are generated by dividing 1 over the standard error of the effect size, or 1 over the variability. So it's called inverse variance. So it doesn't include the variability between studies. It only includes the variability within a study. And in a random effects model, it assumes each study measures a different underlying effect size, and it gives wider confidence intervals than fixed effect model. So the random effect model assumes the studies estimated different effect sizes. Substantial difference in the estimate from both models occurs only if the studies are markedly heterogeneous. So in meta-analysis, when you conduct meta-analysis, you get the tabular summary of the analysis and also forest plots. And you can also get funnel plots and additional information such as Cochrane, chi-square or Q, and I-square, which is a measure of heterogeneity between the studies, which is the percent of heterogeneity explained by the variability between studies. And once you conduct your meta-analysis, you report your analysis results. In your report, describe the study participant, the original studies that are included in your study, the study methods in the primary studies, report your meta-analysis results and interpret them. Discuss your findings and compare and contrast with previous studies, and propose a mechanism of association based on available evidence when there is a significant association between the exposure and the outcome of interest. The validity of meta-analysis depends on the qualities of the systematic review. Based on the statistical software, sometimes you have the outline for the systematic review. For example, the REF-MAN 5 from the Cochrane library has the outline that you should follow when you conduct systematic review. And also there are systematic review and meta-analysis guidelines such as PRISMA guideline or PRISMA checklist, where all the relevant information that should be included in your systematic review and the meta-analysis are listed, and then you have to indicate where those are found in your meta-analysis and systematic review by providing the pages at the right side. A good meta-analysis aims for complete coverage of all relevant studies. So all relevant studies have to be included in the meta-analysis. Sometimes studies that do not find significant association are not published. So you have to make sure you have searched all relevant information and try to include unpublished manuscripts as well, if possible. A good meta-analysis aims for the presence of examination of the presence of heterogeneity. It examines for presence of heterogeneity and try to explain what are the sources of heterogeneity. So once you have conducted the meta-analysis, based on the effect estimate, you run meta-regression where you regress the effect size, the estimated effect size on the potential confounders such as age, gender, years of publication, and other like those of the intervention and the likes. And that can tell us what is the source of heterogeneity between the study. So a good meta-analysis aims for examination for the presence of heterogeneity and try to explain what might account for the heterogeneity, and explores the robustness of the main findings using sensitivity analysis. In meta-analysis, what we mean by sensitivity analysis is we exclude studies that might influence the whole meta-analysis. Some studies have a lot of weight, they overwhelm the meta-analysis. So if we drop those kind of studies and rerun the analysis, do we end up with the same conclusion? So we have to look at that. So dropping studies that might influence the outcome and rerunning the analysis might help us detect if the result is actually biased by just a single study. So when we come to the analysis software, STATA is one of the software. This is enterprise-based software. You can subscribe for a license, and it's not very expensive. R is an open source statistical analysis software. There are statistical analysis packages for meta-analysis. RMAN, REF-MAN 5 is another statistical analysis software. And let's have a look at the example in each of these, short example in each of these statistical analysis softwares. So let's first look at the STATA. So first we have to import the data that we want to use for our data analysis. You can use use and provide the complete paths to where the data is located. The data can be Excel, can be STATA type of data. So we'll use data called VD. It's a STATA form of data. You can also import data, Excel kind of data, text or comma separated value data types and text kind of data, SAS or Excel or from databases, and I use for the data analysis. So once you have imported, we can look at what the data looks like. So go to the data on the menu bar at the top, and data editor. You can see in edit mode where you can change things. So here we have authors, years of publication, a country where the study was published. Here we have the number of participants in the treatment arm, a number of participants in the control arm, duration of follow-up, the dose of treatment, and the different outcomes. So in this study, we are looking at the association between vitamin D supplementation and serum lipid profiles in randomized controlled trial studies. So next, we net search, methane, and install. Net search, methane, and install. So search for a package in STATA that helps to conduct the meta-analysis and then install it if you have not installed before. When we enter this and run, it gives us a number of links where we can click and install the software that can be used for the meta-analysis. So SBE 24 from this link is the one I usually use. It provides us methane, which is a function that helps us to do the meta-analysis. So click on here and scroll down and you will see click here to install. So if you click here and try to install, in my case it says, checking SBE24 consistency and verifying not already installed. The following file already exists and are different says. So no files installed or copied. So I don't want to change it, so I'll just click out of here. But if you have not already installed, you need to install that first before you can conduct the meta-analysis. Once we have installed the methane function, or then we enter our code, methane, the number of participants in the treatment arm, the LDL, the change in low density lipoprotein cholesterol from baseline to end of study, and the standard deviation of the change in LDL in the treatment arm, and the number of participants in the control arm. In this sequence, they have to be in this sequence. The number of participants come first, and then the point estimate and the standard deviation of the changes in the control arm here. And then we put comma here and fix it. This is the the meta-analysis model that we pick. We can include both, fix it at the first one and then second random, but we can also run only fixed or only random. And label the studies with author. And we can also include years, but in our case, years are included along with author, so we won't include year. The X labels, the label for X-axis, and the range of X-axis here. describe that. The aspect ratio, this is the text, the ratio of text to the symbols in the figures, and text, the size, text size here in STATA, and favors here. This is what appears at the bottom on the x-axis as information on the association between vitamin D and LDL. So if vitamin D supplementation reduced LDL at the end of the study, we'll get a negative one. So vitamin D reduces LDL and hash mark. And then if actually the intervention increased vitamin D, when we compare intervention with control, vitamin D increases LDL. And run this. And we get the forest plots and tabular information, tabular summary here. The individual studies, their point estimate, 95% confidence intervals, and the weight provided to that study based on the 95% confidence interval or inverse of the variance. There is no single study that overwhelms in this case. And when we look at the aggregated result, we have the inverse variance pooled standardized mean difference from the fixed effect model, and Damian and Lillard pooled standardized mean difference. They are both quite similar. Like you said, the weights adds up to 100. So the weight times the point estimate, the standard deviation, and finally summing those and taking the average finally gives us the point estimate and the 95% confidence intervals. Let's look at the graph. So the graph shows forest plot here. The horizontal line represents the range of the 95% confidence interval, and the diamond at the center is the point estimate here for the standardized mean difference. And then we have the weight from inverse variance, because that's the main analysis here. And the middle scale bar is proportional to the weight of the study. So some studies, for example, here, it has a very small weight, so the size of the scale is relatively smaller. Other studies have larger weight, and so they have larger rectangle. And some study, one study here is kind of an outlier. It has a larger 95% confidence interval, so it is indicated by an arrow. So here we have the diamond, which is the pooled result, or the aggregate result. From the first one is from the inverse variance overall, and the point estimate is negative 0.09, comparing those that receive vitamin D to those that receive placebo. And the 95% confidence interval ranges between negative 0.17 and negative 0.02. The upper limit is the same. The point estimate and the lower limit are difference between the inverse variance or fixed effect model and the random effect model. The D plus L, or Damian and Lillard overall one, is from the random effect model. So the random effect model considers, in addition to the within study variability, between study variability. So the weights are calculated by dividing 1 by the within study variability plus the tau, or between study variability. All right. Let's see. R. Share R Studio. So now let's have a look at R for meta-analysis. So in R again, let's first initiate a package called Rio that helps us import an Excel kind of data and provide the complete path to where the data is located and import and subset the data. I just want to select quite a few number of studies for this demonstration and initiate the Metan library. So first of all, let's bring the data and subset the data, exclude some data points based on authors, initiate the Metan package, and subset again, select only the first 10 studies, and prepare the meta-analysis. So here we are doing meta-analysis for continuous outcome. Again, we describe the number of participants in the treatment group, the effect size in the treatment group at the end of the change in effect size from baseline to the end of study, the standard deviation, and number of participants in the control group, and the same, and how to name the first column, study lab, author, and then provide the data. Around the forest plot. So again, here, the result and with some options. So we get do plot name and run. So again here, so we just took a very few studies for the demonstration. On the left-hand side, we have the authors. We have the forest plots again. We have the mean difference here. We can change it to standardized mean difference. So since it's mean difference, it's larger. So that means it's not divided by the standard deviation. And we have weights, which is slightly different from before because we have only very few studies here. We have heterogeneity. So in this case, there is no statistically significant heterogeneity. In the previous case in STATA, there was heterogeneity estimated by the I-squared of around 49%, and which was strongly significant. So that means there was a large heterogeneity between the studies. In this case, we only select quite a few studies, so there is no large heterogeneity, and the p-value is not significant at alpha level of 0.05. All right, now let's go to the review manager, a Cochrane Review Manager or RevMan 5 for the systematic review and for the meta-analysis. click the so when you first open the REMAN 5, you see what do you like to do options. Open a review from a file, create a new review. Let's do create a new review. Takes us to a new wizard. Click next. Which type of review do you want to create? An intervention review. That was for us. Let's change the title. What's the title of the review? Vitamin D and LDL. Next. Which stage should the review start in? Let's do the full review and finish. So this opens several windows. On the left-hand side, we have the whole review. We have the title at the top, review information, under which we enter the author information. Let's click on author here. Let's change. Click on here, edit author. Add email and all the information of the author for a correct affiliation to be created. File number, department, all right. Let's add another author. So add author and click on the plus side, it's the add author. And we have empty name here and it's no affiliation. Let's click edit author and do the same. ABC, XYZ, position, professor, email, let's say ABC, UTHSC.edu, department, preventive medicine, organization, UTHSC, and address, let's do Memphis 38103, State Tennessee, USA. And all right, so once this is updated, the information updates here with the affiliations. And the title of the study appears here with the citation example. So for our purpose, let's have a look at the data analysis section. So under every outline, there is subtitle, abstract. Under abstract, we have several other outlines like background, objectives, search methods, what databases have been searched, what are over the search criteria and the likes, and selection criteria, data collection and analysis, main result, author's conclusion, and the abstract. And then the main plain language summary of the findings, and the detailed background or introduction, objectives again, methods, result, discussion, and the likes. Let's go under the studies and references, included studies. Let's add included studies. David 2012. So add the last name of the author and the year of the publication and click next. You can select published data and unpublished data or published data only. It's based on what criteria you used. Next, the year is automatically selected. And here, PubMed identifiers of the article. And what do you want to do after the wizard is closed? Add another study in the same section. Continue. Chart 14. Add another study. Even 2015. Add another study. June 2017. Let's finish. So under data and analysis, let's right click and add comparison. What name should the comparison have? Vitamin D and LDL. Next, what do you want to do after the wizard is closed? Add an outcome under the new comparison. Continue. What is the outcome? What type of outcome do you want to create? So the data type, whether it is dichotomous or binary outcome, where the outcome is yes or no, or 0 or 1, continuous as in our case, low density lipoprotein cholesterol, which is measured in like milligram per deciliter of blood, or observed and expected and variance in case of survival analysis, and generic inverse variance or other data. So continuous in our case, where we enter the mean and standard deviation and number of participants in the intervention group and control groups. Next, what name should the outcome have? Let's say LDL. Change the label for group 1 as vitamin D. Add placebo or control here. Next, which analysis method do you want to use? A statistical method. We want to use inverse variance. And the analysis model, let's go with fixed effects first, and then we can change it by clicking on options for the graph. And the effect measure, let's estimate the mean difference first. We can also change it to standardized mean difference. Next, which analysis details do you want to use? Total and subtotals, subtotals only, no totals. This means the aggregate or pooled result. If you do sub-analysis when you have larger number of original studies, you can do subtotal only if the subgroups are not similar and you don't want to pull them together, or if you want to pull together total and subtotal. In this case, let's do the totals and subtotals to get the total for our 4 studies. The study confidence interval, this is based on the original study. Let's do 95%. And total confidence interval, again, 95%. Next, here, which graph details do you want to use? This is if you want to edit the x-axis level. So when the point estimate is to the left side and to the left side of the 0 x-axis, the result favors vitamin D. D lowers, it's negative, so after the study, it lowers LDL. FT is on the right side. When we compare the intervention group and the control group, D increases LDL. And how do you want to sort the study? Let's sort them by year. And next, let's go back and do the scale. Let's do the change, the scale for the change, let's say 10 or 15. Next. And what do you want to do when the wizard is closed? So the wizard is completed. What do you want to do after the wizard is closed? Edit the new outcome. And finish. So as you see, no studies added yet, but we have study added to the studies and references. So we can come here, and on the right-hand side, we have a window where we can add included studies. So we have 4 studies here. We can select all the 4 studies by controlling command in Mac OS or control in Windows computers. And finish. So as you see, there is no data in there, everything is 0. Let's click on each and change them. Let's say after the intervention in the David study, the mean LDL increased by 10. The standard deviation was, let's say, 3. The total number of participants was 120. And in the placebo arm, let's say the mean increased by 12. Standard deviation was 4. Total number of participants was 120. In the Richard study, let's say the finding was that they found LDL was reduced to 7 after intervention. Standard deviation was, let's say, 2.5. The total number of participants was 110. In the control or placebo arm, the LDL was reduced by, let's say, 3, -3. Standard deviation was, let's say, 4. The number of participants was 105. So this is based on the data from original studies. We don't randomly add this information. We get this information from the original studies that we got from our search. Let's say under the Stephen, there was a reduction of 3 in the vitamin D group. And standard deviation was, let's say, 1.8. Number of participants was, let's say, 140. In the placebo arm, the reduction was, let's say, there was an increase by 2. And the number of participants was 135. Let's say 2.3 standard deviation, and the number of participants was 135. For the John study, let's say the mean difference was 7. There was an increase in LDL, and the standard deviation was 3. Number of participants was, let's say, 90. In the control arm, the mean difference was, let's say, 5. The standard deviation was, let's say, 2.1. The number of participants was, let's say, 90. So as you see, we have a figure on the right-hand side, which is updated whenever we enter the data. And we have the heterogeneity information and the test for overall significance of the pooled result. So when we click on the forest plot here on the right-hand side, the whole information appears. So looking at the heterogeneity, the chi-square, and degrees of freedom, we have 4 studies, and the degrees of freedom is 3, 4 minus 1, and it's highly significant. The I-square statistic, which is also the proportion of variance is explained by heterogeneity, that's 99%, very high. So we cannot use a fixed effect model, so we have to use a random effect model. We can change that by clicking on the FE here. Let's change that. So as you see, when we change it to fixed effect, it's highly significant. When we change to random effect, it's kind of borderline or not significant. The pool result or the total result is not significant. We can also change to the standardized mean difference. For the random effect model, that's the kind of borderline, as you see. Let's random effects and mean difference. So for example, standardized mean difference, you can rescale it by coming here and under graph, change this to, let's say, 10. Now, we have rescaled it. We can even rescale further for the standardized mean difference, but let's go with the mean difference. So we can click on the forest plot here, and we can either save the forest plot on our computer and use, if we are creating the whole review in Microsoft Windows. But if you are doing the review under the RefMade and you want to include here, you can include the figure by add as figure. But let's save it in our case. Let's save it as scalar vector graphics, which is SVG. If you save it as PNG, the data, the figure will be kind of distorted. The resolution is not good enough. So I suggest to use the scalar vector graphics. Save on downloads. Yes. All right. Let's X out of here. Minimize, stop share. Let's open a new share. Let's open. So this is what the forest plot looks like. So the horizontal line stands for the 95% confidence interval. The central square is proportional to the weight of the study, the weight that's provided to the study. And at the bottom, we have the diamond, which is a pooled result that's found at the bottom here. So it includes 0 across 0, so it's not statistically significant as indicated by the total, the test for overall effect, p-value here. We have the I-squared stated here. Thank you. All right. So thank you very much. If you have any question, please email me at ddibaba@uthsc.edu. If you have any question, please email us. If you want to meet us for bird clinic consultation for your study for data analysis, please go to tnctsi.uthsc.edu, and you have the links there to reschedule to schedule a meeting and to meet one-on-one with a team of us at University of Tennessee Health Science Center, Preventive Medicine, and Tennessee Clinical and Translational Science Institute. Thank you.